Enabling edge computing deployment in 4G and beyond. The fifth generation of mobile networks will be the driver for new vertical business models involving all the stakeholders, from vertical industries to over-the-top providers and software developers. Edge computing has been widely accepted as a key technology to bring application-oriented capabilities within telecom operator infrastructures, much closer to end users and so enabling new use cases thanks to the available information of the user location. 5G networks natively have functionalities available for edge computing integration. Instead, 4G was not conceived to support edge computing and has a number of issues related to user plane integration and to isolation. Since 4G network will still exist for several years, their integration with edge computing is desirable to allow for a smoother transition to the new technology. In this paper, we address the deployment of edge computing in a 4G network and also provide some insights on the potential application to 5G as well. The paper describes the endpoints, realized as virtual network functions between the mobile and edge environments, and the orchestration mechanisms to horizontally scale the VNF instances according to the traffic load and to all associated QoS class identifiers. Since the original ETSI-MAC reference architecture was defined to suit any mobile networks, stakeholders can benefit from the business opportunities fostered by edge computing while still relying on 4G networks. Still, edge computing solutions have to be designed as add-on features to 4G networks, and there are issues related to user plane integration and isolation of tenant spaces. For example, application components running in different data centers require NFV services for interconnectivity. But since the app components and the VNFs of such network services may be hosted in different Vim tenant spaces, the traffic exchange among them is not easy unless some so-called attach points are in place to help exchange traffic among isolated tenant spaces. Among the functionalities defined by the 5G core specifications, the UPF realizes all the user plane operations. Applications can determine the forwarding rules to steer predetermined traffic flows towards an external data network that can be seen as the attach point between the application and the network domains. 4G network specifications don't allow exposing reference points externally to realize these attach points. So, additional functionalities are required to expose the S1AP and S1U protocol interfaces. Among the existing solutions, considering how the location impacts on the performance, we have chosen the bump in the wire solution, in which the attach point is between the node B and the EPC, very convenient in the present of a CRAN deployment. We have implemented a bypass VNF that defines flows on a per bearer per take basis. The solution can be ported to 5G, as the design and even the code of the bypass VNF are suitable to be deployed as UPF. This slide represents the main functionalities performed in the bypass VNF. The identify function intercepts S1AP messages and parses their content to univocally recognize the UE, the node B where it is attached, and handover events. If the intercepted packets do not belong to any of the deployed applications, they are directed again to the EPC without any further operations. Then, the bypass injects and retrieves the GTPU packets from the S1U protocol. This function also realizes the actual endpoint between the edge application and the RAN by removing the GTPU from the identified packets and ending the VLAN tag. Finally, a virtual gateway is used to check the tag and forward the packet to the corresponding application endpoint. I want to spare you the mathematical model in the paper for the orchestration policy and just provide a quick description. We consider one data center. Its CPU, RAM and memory capacity constrain the maximum number of bypass VNFs that can be instantiated. Users are characterized by their load and by a latency requirement, which is the most stringent among the apps of the user. The objective of the orchestration is to find the minimum number of VNF instances required to process the incoming traffic. By interpolating the characteristic curve of the bypass VNF, we obtain the latency as a function of the load and can determine the load upper bound lambda star for any given latency constraint. We have done a number of tests to assess the behavior of the proposed edge computing deployment. The first measures have characterized the delay between the UE and the destination of its traffic ascribable to the presence of the bypass VNF. The testbed is composed of a traffic generator and two servers. The transmitting port of the traffic generator behaves as a UE, and the receiving one represents the endpoint of the traffic. Latency is measured between these endpoints. The first server hosts a VM for the GTP encapsulation to emulate the behavior of the S1 new protocol, which is not available in the traffic generator. The second one hosts a VM that contains one instance of the bypass VNF, which performs the operations I described some minutes ago. This graph reports the latency ascribable to the VNF processing. Traffic has been transmitted at increasing rates from 10 to 200 kilopackets per second, with packet sizes set to 1440 bytes. Latency is sufficiently low to satisfy the delay budget of all the services defined in the 3GPP standardized QCI characteristics. Considering standardized 5QI values, it is still sufficient to handle almost all of the use cases under the URLLC umbrella up to 10 milliseconds. As I said before, this characteristic curve can be interpolated to get the load upper bound for any given latency constraint. In order to test the outcomes of the orchestration policy I previously introduced, we have considered two simple mechanisms and compared their impact on the system occupation and the latency. The first case, case A in the results, minimizes the number of VNF instances without discriminating on the specific QoS requirements of each bearer. So traffic is shared on a per-tape basis among a number of active bypass VNF instances whose lambda star is the same and is set to the most stringent latency requirement among the hosted applications. The second case, case B, instantiates subgroups of VNFs for each QCI that receives traffic from the corresponding bearer. In the test, we consider a number of bearers varying from 100 to 1000, each one with a random traffic rate between 1000 and 2000 packets per second. These rates come from the Cisco VNI mobile speed forecasts. Each bearer corresponds to one of the applications in the table, which have been selected among the 3GPP use cases to provide heterogeneous latency requirements. These are the traffic load shares among the number of VNF instances for case A. In this case, the policy adds a VNF instance when the available ones reach the value lambda star of incoming load, which for this test case is the most stringent among the apps. As the traffic grows with the number of tails, the optimal allocation corresponds to an even share of the traffic among the available instances. For case B, the number of VNF instances depends on the traffic ascribable to the individual apps rather than the aggregate. So, now 3 instances share the traffic from the bearer associated with app 1, leaving the remaining 2 VNFs to handle a higher traffic volume with lower latency requirements. The number of VNFs required in case A is higher for higher loads with respect to case B, but for lower rates there is a significant saving of resources, with 5 VNFs active throughout the whole test. We have also computed the average latency ascribable to the bypass for the 2 cases. Since in case B bearers are associated to specific QCIs, the average latency is also reported on a per-app basis in addition to the average one. Case A provides lower average latencies for a number of UEs above 400. In fact, for this load, we saw in the previous slides that the number of active instances in case A is higher than the one in case B. However, the latency obtained for the traffic associated with the app1 QCI requirement in case B is always lower than the one in case A. The policy of case A scales better with the number of bearers, and on average it allocates a lower number of VNF instances. However, case B has better granularity and can fulfill heterogeneous QCI requirements even in the presence of huge amounts of traffic. In fact, above 800 tails, case A provides lower latencies, but it needs to instantiate 3 more VNFs, while case B uses only 5, respects the desired QCI requirements, and even provides better latencies for app1 and app2. This aspect is quite relevant with the growth of mobile traffic, the heterogeneous requirements of the use cases, and their low latency requirements that will be fostered by 5G. In this paper, we have proposed a solution for the deployment of edge computing in 4G networks. We have designed the endpoint between the access and the edge networks in a VNF to intercept and forward data and control traffic to the applications in the edge network. The VNF instances can be horizontally scaled according to a decision policy that determines the minimum number of instances required for a current load. Results have assessed that the bypass VNF can satisfy the delay budget for the 5G use cases up to 10 milliseconds and can fulfill the performance requirements of each application when horizontally scaled. Thank you for your attention. If you have any questions, do not hesitate to send me an email.